The data files which I am going to use are rather big, but still I have put it on the website, and it is called root stuff 3. So it will take you some time when you are trying to download it because the files are big. Anyway, this is after unpacking. These are the files. So after you have unpacked root stuff 3, then the files which you get are here, except for one or two files which will come after you start the analysis. So for example, this file will not be there when you unpack, and these two CSV files will not be there, and nor will this executable be there, but they will arise after you start your work on this folder. So this folder consists of some actual data. So there are two root files here with Californium 252. This was actually taken in November 2019 when the data acquisition system NIAS was first set up with a controller which has been made by IUAC in VME, and this was installed in NAND, and I was also there. And in fact, my students of that year were also there, and the students were invited to participate in that experiment in which we acquired the data. And then along with the students, we analyzed the data. So today we are going to do that with you. So the experiment itself is explained here in this presentation. So this was basically a test run. The NAND setup at IUAC consists of around 100 neutron detectors, but we wanted to do a small test run. The test was not of the NAND itself, but of the data acquisition system, new one being installed there, because previously LAMPS was in use up to 2019. In 2019, IUAC made their own controller for VME, and it was decided to shift over from the LAMPS VME system to the ROSE NIAS system. This ROSE NIAS system has been described to you in a presentation which most of you would have attended, which was given by Mamta. So now in today's lecture, I am going to explain to you what that ROSE NIAS data looks like and how we will analyze it. And also, this is your first exposure to actual data taken in an experiment. Once again, this is a simple experiment. This doesn't have all the 100 detectors, but only 2, so that you get an idea how to analyze. Of course, if you know how to analyze with 2 detectors, you also know how to analyze with 100 detectors, because the procedure is the same. So this becomes a good learning tool. So what was done is that, because this was the first test and it was done without any beam, so if you don't have beam, then you can't actually get any data. So to get data, we did it by putting a Californium 252 source, which is fission and neutron source. We are using it here as a neutron source. The detectors are neutron detectors. So we pulled out 2 detectors from the array and kept it on the floor, and we kept these 2 detectors facing each other with a distance of 55 centimeters in between. And the Californium source, shown here in red color, is kept very close to one of the detectors, just 1 centimeter away from the front face of detector number 1. And the reason is that this is basically neutron time of flight, this method. So with such a source like Californium 252, which is a very expensive source, but unfortunately it's not a very strong source, not strong enough to get a good counting rate. To get good counting rate, you have to bring it close to the detector. But if you bring it close to the detector, like in this one, we have brought it so close to the first detector, distance is only 1 centimeter. So count rate will be very high, but the distance is being small, the neutron time of flight will not be possible. So the time of flight requires more distance. But time of flight will be possible for the second detector, because the neutrons are going to travel from the Californium source over here, and it will travel this distance of 55 centimeters flight path before it reaches the front face of this detector. As far as the distance is concerned, we are going to add half of the width of this. So this detector depth is 5 inches. So if you consider half of it, 2.5 inches, that is 6.35 centimeters. The distance of the californium source to the center of this detector will be taken as the distance or flight path of the neutron, and that we will take it as 61.35. So as mentioned, D1 flight path to the first detector is only 1 centimeter, so time of flight will not be possible for detector number 1. And here we have used detector number 1 as a trigger. So yesterday we had talked about this cobalt 60 experiment. This is similar to that, but this is done with neutrons, not with gamma rays. In fact, the source emits gamma rays and neutrons both, and the detectors are sensitive also to both neutrons and gamma rays. So it's neutron and gamma, although we are interested more in the neutrons, but gamma rays are also detected, and the number of gamma rays is actually much more than the number of neutrons. So if you look at this first detector, it will be triggered basically by essentially gamma ray only, rather than a neutron. And then in coincidence with that, the neutron which we want to detect, also gamma ray will come, but we are interested in the neutron. The neutron will have this much flight path, 61.35. So the neutron will travel from this source up to the second detector, and we will try to construct the neutron spectrum. So our exercise is to construct the neutron spectrum in detector number 2 based upon time of flight. And the way that we discriminate between neutrons and gammas, it is called as pulse shape discrimination combined with time of flight. So pulse shape discrimination, for those of you who don't know, is because the detectors, these are liquid scintillator detectors, BC501A, they are sensitive to both neutrons and gamma rays. But we don't want gamma rays, we want neutrons. So how do you distinguish? So the pulse shape is different. So for the two type of pulses, gamma rays and neutrons, we make use of that and try to choose those which have got the pulse shape as expected for neutrons rather than the pulse shape which is broader for gamma rays. So we choose the pulse shape signal. We take out the pulse shape signal. This is done by some electronic processing called the pulse shape module, not shown here. So we collect the pulse shape signal, and we also collect the timing signal, and from the timing signal, that is the time of flight, as well as the pulse shape discrimination, we will select the neutrons, and to find out the neutron energy, we will use the formula half mv square, where m is the mass of the neutron and v is the velocity. And consider that the time taken for the neutron with a velocity v will travel over the distance of 61.35 centimeters. So this is the experiment, and then the data was collected. Naturally the files are big, so I have brought for you two of the files here. I even put them in my website. The files are big, so when you download it will take some time, but let's go ahead with that. The names of the files are 252 californium underscore 6th November. This was the date on which the experiment was done, and then the name given is .001, .002. So the convention in this NIAS system is that the first file will be having this .001. Then when it is continued, the second file will have .002, and like that until you decide to stop and then change the name also of the run. So this is how they take. But actually these are, this 001 doesn't mean that it's a candle freedom type of file. The format is not that of candle freedom. So earlier on, when the data used to be taken in IUAC using the CAMAC candle system, that used to be also called .001. So we used to use, and everybody knows that .001 means it's a candle format file. But now with NIAS, they have not changed that, and they are still giving the name .001. but these are actually root files. So what I have done, and I think it is good, I just changed the name like this. So what was done with .001, I removed the first dot, and then I have put .root at the end of it. So the files which you will see in the directory, they will end with .root. So not that you have a problem if you don't change the name, also you can do the analysis. The same analysis which I am describing now can be done even without renaming the file. But at least now when we are beginners, it's better that we put the .root so that we are not confused about the type of file it is. The name of the tree inside this, earlier on we have been working with something called LAMMPS tree. That's because we were doing the conversion of the data using the LAMMPS program, but now we are not doing that. So this data is taken directly from the Rose NIAS system. So the name of the tree is going to be Rose NIAS. And this experiment was done with only 2 detectors. Actual experiment is done with 100 detectors. So here the system will the way that this system works, it is geared for all these detectors, and these are the VME modules. I have listed them on the right. So there is one ADC. Each ADC in VME has got the possibility to collect 32 signals. What we were earlier calling as sub addresses, they go from 0 to 31. So there are 32 signals which can be put on a single ADC, and the first ADC will be called ADC01. It will have 32 signals. The second, then after that in the VME crate, the next is a TDC, and for collecting a timing, and that is called TDC1, and that is also having 32 signals. After that, next ADC is put, and that again has got 32 signals. Then again there is another TDC, and that is again having 32 signals. Then followed by that there is another ADC with 32 signals, then another ADC with 32 signals, and then there is a TDC again with 32 signals, and then 2 more ADCs. So this is for the real data that we will require so many ADCs and so many signals. But for this first run with NIAS, we did not connect all the signals. We connected only 2 detectors, and they were placed in these positions. So the detector 1, the pulse shape discriminator output, was put in ADC number 6, and in the 16th position. As mentioned, there are 32 positions possible inside each ADC. So the PSD 1 was put in the 16th position of ADC 6. So this is ADC 6. And the second detector was put again also in ADC 6 in the 17th position. And similarly, the time of flight of the first detector was put in the 16th position of TDC1, and the time of flight of the second detector was put in the 17th position of TDC1. So this is the basic information. We will also show you how you can collect this basic information from your side by probing the data. So let's go to what we have to do. So this is basically, if you want to run quickly root on this type of file, then this is what you have to do. Go to the command line, set up the file name as we have learned, then take a list of it, and then it will tell you that the name of the tree is Rose NIAS. So you will come to know the name of the tree by printing it. Once you know the name of the tree, then you will find that these type of ADCs and TDCs are listed inside it. Of course, you do not know where the signal is connected. That you will know only if you participate in the experiment. So for us who participate in the experiment, we know that only these signals are there. The rest are not even connected, so there won't be any data there. But 16 and 17 in ADC 6 and in TDC 1, they are the place, and these are the 4 signals. So this data, of course, cannot be found out by looking at the data unless you look at all the channels and then try it, and there are so many, and then only you find that okay, so the data is in this channel. So that will take a long time, but we don't do that. We have participated in the experiment, so we know that the detectors were actually connected at these places. So you can draw these spectra by these commands, and if you want to draw 2-dimensional spectra, then you know that you have to put the X and then colon and then Y. So you can draw the two-dimensional spectra of PSD versus time of flight like this. But then you know that this is only for your first quick look, and this is not going to help because you have to build spectra. We have to make an event loop. So this we have learned in up to yesterday. We learned how to do the event looping, and this all is only for quick look at the data. It doesn't help for real analysis. So now you encounter that this is real data. If you feel that only these much commands I have to learn and I can do the analysis, no, it doesn't work. This is only for quick look at the data and doesn't give the histograms of the required resolution. Instead of that, we have to write a macro or a full program, and in that this is the information we need in order to write that full program. And writing the program you will become quite conversant with after today's lecture. So now you already know more or less, based upon whatever I have written in this slide, you should be in a position to write the root macro or the root full program on your own after looking at this PowerPoint. That's the state. Of course, today it will be done for you and you will have the file. But think about it that tomorrow or another day, you will have to write the root file, root processing file on your own with only this much as a input. So you should know how to proceed. So that is what we are covering today. And finally, the aim of this exercise is to construct the neutron energy. So the neutron energy, as I mentioned, it is to be calculated from the time of flight. So the distance to the detector is 61.35 centimeters. So we will set the D equal to 61.35. And then we will calculate time of flight using this formula. This I will explain slowly what it is. So TTC 0117, this is the actual time which is collected in the TTC. And then we must subtract this number 2906 because this is the position where the gamma ray comes. This I will show you. This is the channel number of the gamma peak. So we use the gamma peak as a reference mark because the gamma travels at the velocity of light. So we know how much time gamma rays will take to travel this distance, and the time taken by gamma rays to travel this distance is given by d over 30, because 30 is the speed of light in centimeters per nanosecond. So we will be working in the units of centimeters for distance, and for the time the unit will be nanosecond. So d over 30, that will be the units for that will be the time of flight for gamma ray. So then we subtract 2906, which is the position of the gamma ray in the spectrum, and then this factor 800 divided by 4096, this is it's called as the TTC calibration constant. And this is because the TTC has been set to have 800 nanoseconds full scale, and 4096 is the maximum channel number. So it comes at so if the channel number comes 4096, what we mean is 800 nanoseconds. So that's why we scale it by this factor. So this is your calibration factor of the TTC. This 2906 is the position of the gamma ray peak, and this is the time that gamma rays would take to reach the detector, which we must add on. So the neutrons are slower than gamma rays. So this time of flight recorded in the TTC will be larger than 2906. We will get a positive number here. Then it will be scaled by this factor, which is going to convert from channel number into nanoseconds. And then we add this much time because this is the amount of time that gamma rays would have taken to reach, and we have used gamma ray as a reference pointer. So we must add the time that the gamma ray would have taken to cover that distance. So this is the basic formula, and then once you have this, then you know the rest how to calculate. First you calculate beta, which is v by c of the neutron. The velocity of the neutron is given by the distance divided by the time of flight. And if I wanted b by c, making it dimensionless, so I divide it also by 30. 30 is the velocity of light in centimeters per nanosecond. This gives me beta. Beta is the v by c of the neutron. and then I need to calculate En, which is the neutron energy. It will be half mv square. We can rearrange the formula as half of beta squared into the mass, energy equivalent of the mass, and we know that the mass of the neutron in energy units is 939.56. So the final formula is rather simplified like this. So there are some people who, they work with different units and they get confused. So don't do that. Always use mass of neutron in MeV units, and put the velocity in a dimensionless form, that is beta. Then the formulas are easy to handle. And one thing you have to be careful, that this time of flight is coming in the denominator, TOF. So this has a danger that if TOF is 0, then the program will crash. So you can see here. So this is possible that TDC 0117 has exactly a value of 0, which will happen for the gamma rays. Near the gamma ray peak, it will happen a lot. So in that case, the TOF will be 0, and then when you try to do D divided by 0, then the program is going to crash. So you have to take care of this in your program and restrict to the case when the time of flight is positive. Taking time of flight negative is also not very meaningful, because it means the neutron is traveling faster than gamma ray, and gamma rays are the traveling with the velocity of light, so nothing can travel faster than light. But there will be some data which is coming ahead of 2906, and that is actually the tail of the gamma ray due to resolution. So those events will give negative numbers. That also we have to avoid. So with this much introduction, I pass on to the actual data analysis work. And for that, the work is divided into two phases. The first, I should say three phases. The first phase is totally exploratory, where you have got this file, and let's say you don't know anything about the file. So this process has been explained to you earlier, how we identify the parameters in the file. Now this is a real life situation. You have done the experiment, you got the data, and you are trying to find out the parameters. So these are the two data files, and the process is you right click and then open in terminal. So this is my terminal which I have opened, and now we will start root. So root has been started. Now having started root, the next thing we are going to do is to open the file by the usual TF equal to command. You can also do it with the T browser, which I have shown you earlier. I am not doing that again. Let's directly go to this TF method. So TF is equal to a new T file, and then you give the name of the file here. So the name of the file is 252 Californium. to Californium underscore 6th November, and let's take the first one, dot root, and let's attach this file. So TF, this we attached. Now you know the next command. We do in order to discover the name of the tree which is inside this, we do the ls command. So the ls command will reveal to us the name of the tree. So having done that, he gives it here. So the name of the tree is Rose NIAS. So having discovered the name of the tree, now we are in a position to print it. So the command which is also explained to you in the PowerPoint is here for you. If whenever you need, you can refer. You need to give the name of the tree, and then with an arrow you have to give the print command. So we give the name of the tree, Rose NIAS, and then we ask for the print, and then this is what we get. So you see that the list is it starts here. So I told you that it consists of several ADCs. The list was again given in the PowerPoint. So the list was given here. This is the list. So you may now notice the benefit of dimensioned leaves for the first time. See, up to now what we did, the leaves were having names, but these are the names of the leaf. But there are 32 leaves with this name. So the leaf has been dimensioned and it is made into an array so that we can deal with a large number of quantities. If we give separate names to all of them, then the list will be too huge. So in NIAS-IUAC system, this idea has been followed. Now this is not universal. Some people follow this idea in big systems, some people do not. But mostly when the system size is big with many parameters, this convention is followed. So in this convention, when you list it, he will explain that there is a leaf here, but he will not write this leaf 32 times. There are 32 leaves here, but it is in the form of an array. This D means now it is of type double. Earlier on we have seen type S. This is of type D, that is double. And then also important is, as I mentioned, that there are 32. So the list consists of the only this way. The list is relatively short, and it ends up with, there is also one NIAS info which I am not going to talk about. But up to ADC6, this was listed in the PowerPoint. These are the name of the parameter. Each of these parameters are having 32 leaves in the form of an array. We are going to read only 4 quantities, but there are so many. So now you may refer again to this PowerPoint to see what you are supposed to do. So we finished this print command. Now we know that the data is sitting in parameter 16 and 17. This one is your, this command is your pulse shape discrimination signal for detector 1. So this command is, I am pasting it here. This command will actually show a plot of the pulse shape discrimination signal. So the pulse shape discrimination signal looks like this. So this first peak which you see, narrow and broad, these are actually gamma rays. And this second part here, small peak, this part, the second part, namely from here to here, this is gamma rays. Sorry, this is neutrons. The first one is gamma rays and the second one is neutrons. So this pulse shape discrimination signal is used to separate out neutrons and gammas. But it's not perfect. Pulse shape alone doesn't distinguish, because there is a region in between also in which you cannot tell whether really it's a gamma ray or a neutron. So that's why we don't rely only on pulse shape discrimination. We also make use of time of flight. So let's see what the time of flight looks like. But here in this detector, because the distance is only 1 centimeter for the first one, the time of flight will not come out properly and we won't be able to use it. But we can draw it. You will see that it has got only one peak. So this is in TDC 6. In TDC, let me check where it is. It is in TDC 01. It is in TDC 01 and it is 16th parameter. So TDC 01, 16th parameter. And what happened is that it, sorry, so this is to be written as, the name was wrong. Yeah. So this is your TDC parameter. You can see that it has not done the binning properly, and you are getting a very funny, actually this peak was very narrow, and then so he made many bins which he should not have, and then he split it up like that. So these draw commands, they don't work for you. We have to write our own program and make the binning ourselves. This you know already. But anyhow, this is the picture he has given, which is not helping us, but just shows that this is the data. So you can do the same thing for the other detector also. So they are in, so the pulse shape discrimination is in the 17th position. So this is sorry, what did I do here? Yeah, so let's start with this one. This is the pulse shape in the 17th position, and this is looking like this. Now when you see this, now you know, you don't be surprised when you see this is due to the auto scaling failure, because this has scaled it similar to what I demonstrated earlier. There are so many triggers are there because the first detector gets very close, the californium source gets so many triggers, second detector gets much less count, so that peak is actually here. You cannot see it, but if you zoom it, then it is visible. So I need to unzoom and zoom it better. So all you have to do is to avoid actually the first portion. Unzoom. See, so I start from here and do it. Now you see, you can see it clearly, but the counts will be much less compared to first detector, because the detector is very close to the source for the first detector, and for the second detector it is quite far. So that's why the counts are small. Okay, then similarly we can see now the time. So in order to see the time, we have to see this one, and this looks like this again. You know, you can, this auto scaling problem, so you have to zoom it like this, and now you see in this case there are two peaks, whereas when we did for the previous detector, although that it didn't come out properly on the screen, you will see later on there's only one peak there because it's too close, but here two peaks are there. The first corresponds to the gamma ray and the second peak corresponds to the neutron. So neutrons are slower than gamma rays, the time of flight is more, and it comes on the right. The first peak is gamma, coming at a smaller value of time of flight. So this was the first probe of the data, and this first probe of the data I have mentioned earlier is of no use. It doesn't help you to analyze the data at all. Just giving you a quick look. What you have to do is to create either a macro or a full program. So what we are going to do, and this you will have to do in your actual data, always write your full program, but write it as a macro. So we showed you already how you can write a macro which can also be used, you can write a full program which can also be used as a macro. So you write it in that way and use it as a macro only in the beginning, and if required to analyze many files, then only you convert it into a full program. Here we have only two files to analyze, and the time taken for analysis is very small. So even if we don't bother to make it into a complete program, we can manage to run it only as a macro. That's also okay for such a small experiment. But in a real experiment where there will be many files, the time of analysis will be large. So if we can make it from macro, we can go into a full program, then the situation will be speeded up very much, because full programs, they run much faster than macros. So let's see what is the macro. The macro that we are going to work with is called explore.cp. We will do it in two steps, two more steps. One step is over, preliminary probing. That step is done, preliminary probing is completed. Now we have to do writing a macro or a full program, but still we are not yet in a position to do the last step of analysis, generating a neutron spectrum. That will come in this one when we write the second macro. The first macro or full program will be exploring the data in order to decide what kind of gating and what are the procedures we require in order to finalize. Final aim is to obtain the neutron spectrum from time of flight. But right now, let's first explore. So this is the program which I need to write. Now, the way that this program is written is same what you have seen. There is no change compared to what we did yesterday. So there is, this main program is just like this. And here you give a name, and this name must be the same as the name of the file, and it should also be the name of the function which is it calls over here. And then what you have to write, which is different than what we have done before, is only for this particular problem, is all sitting from here to here. So everything which we are doing is only these many lines. So what are we doing? So first we declare the ADC and TDC where our data will go, because we are going to have a event loop. See, this event loop was introduced yesterday. We discussed it. Before that also we discussed it for 2 days. So we have to make an event loop like this. And I am introducing one or two new concepts which will be useful. They are easy. For example, let's take this. So this is histogram 1. Type I have chosen I. I give it a name histogram P1. So it's pulse shape discrimination signal for detector number 1. So HP1. And then here is the title. Now notice here that this I have used a LaTeX style of writing it. So this is something new, not introduced earlier. This becomes a subscript. So PSD subscript 1. So you are allowed to use LaTeX like symbols inside the these kind of definitions, so that on your canvas when it is drawn it will look nicer. I mean, you could have called it PSD1, but he has got the possibility to call it as PSD subscript 1. And for that the command is, for those of you who are familiar with LaTeX, this is the type of command that you have to write. So I am here defining first the four single one-dimensional histograms. That is pulse shape discrimination, time of flight for first detector. Then pulse shape discrimination, time of flight for second detector. Then I want to do pulse shape discrimination versus time of flight. I want a two-dimensional plot. So this is for the first detector and this is for the second detector. So all this should be easy to understand, but now comes another command which I have not introduced earlier. Earlier on at this point we used to do TF and we used to open the file. But now I want to analyze two files. So there is here a command, it is called as chain. So it allows you to, suppose not only two, you have many files. So it allows you to analyze all the files in one go by placing them in a chain. So I decided to, the other way of doing it is to do them one by one. So instead of making a chain, you can finish one file and then you can loop it and go to the next file. But this is the better way. So I am introducing this idea of the chain because in real analysis you will require it. So if there are many files and they are to be combined into one analysis run, then you use this tchain command and you put the name of the two files one after the another, just like this. So this completes the chain, and now as yesterday introduced, you have to print out the number of entries. But now when I ask him to print the number of entries of the chain, he will print the total number of entries in this file plus this file. It won't be the number of data in the first file only. It won't be the number of data in the second file only, but it will be the total of the two files. So this will get filled up here. And now this, you remember, we used to set the branch address. Now this setting up of branch address becomes easy because of course here we have only 4 signals, but in real data when all these ADCs are populated, so you have 32 here, 32 here, you have more ADCs which are not written in this case because they are not being used. So when you do set branch address, even this one actually assigns 32 branch addresses in one command because of this leaf array system. So because the leaf is an array with 32 channels, so it becomes easy to make only one command, and this is equivalent to 32 commands. Otherwise, if it was not having, this leaf structure was not having an array, I would have to type 32 such commands in this one after the another, and for this also I'd have to type and this 32 commands, and this would be repeated for all the other ADCs and TDCs. So this part of the code would become quite long. So that's why this method is used, in which the leaves are made into an array. So this takes care of the setting of the branch address. Now we just make a loop over the events like this. So this is my loop array. As soon as I execute the first command, get entry, earlier on it was operating on the file, now it's operating on the chain, but idea is same. As soon as this command is over, then these quantities will have values, and those will be the values which are stored in the tree. So having got the values, then I fill the histogram. So this you know how to do. It's no different than earlier, except that here we will fill for particular data where the data is located. So this one will be pulse shape discriminator 1. This one will be time of flight detector 1. This one will be pulse shape discriminator 2. And this one will be timing signal from detector 2. And then this one will be on the x-axis, it will be the pulse shape discrimination signal. On the y-axis, it will be the timing signal. Same for this, for the second detector. So this is it. This is a preliminary probing of the data. We are just taking the data as it is, not manipulating the data in any way. So we don't yet have any information about calculation of the time of flight using that half mv square formula. That is yet to be done. So at this stage we are just plotting the raw data as it is for two of the detectors. So in your real NAND experiment, this is exactly the same file you have to use in exactly the same way. Only difference is, instead of having two detectors, you will have about 100 detectors. This is the only difference, but in other respects the situation will be same. So now, having got the histograms filled, this you know that we just make the canvases and we draw them, and that is the end. So this program is not very different than what we have already learnt, and so you should be in a position to write such a program on your own by using these examples and having the example always in front. Without having the example in front of me, I also cannot write the code for some other example. I need to have this file with me, and then I want to cut and paste from here and then make changes as required. Just starting absolutely from zero and remembering everything, it is not possible for anybody to do it. So always have these files with you as a reference material, and then you can definitely change it according to any other experiment by making the required changes. So that's it. Now we have only to run. So let's run it. Now this can be, now since I have put this conditionals here, this can be run either as a full program or as a macro. Both ways it will run. So if I want to run it as a full program, then I need to compile it first, and if I want to run it as a macro, then I don't need to do anything, just run it as it is. So let's run it as a macro. That will be okay for us. We will not make it into a full program for now. So ideally I should now close this root session and start a new one, but since we haven't done too much, we can probably go ahead. So I am going to just keep this source code here in front of you so that we can refer again to it. I am going to make this window smaller so that this much space I leave for my spectra to appear, and there are going to be 6 canvases, as 6 canvases are defined here. There will be 1, 2, 3, 4 one-dimensional spectra, and there will be two-dimensional spectra. There will be 6 canvases in all. So you know how to do that. So you say execute and then give the name of the macro, that is explore. So this is your macro execution command. If there are mistakes, now writing this macro, right now it will run because there is no mistake. I have already tried it out, so it's okay. But when you write this, there may be mistakes. So when you run it, the mistakes will be shown over here, and then you have to gradually correct it until everything is okay. So I'm going ahead. This is mistake free already, so in one go it runs. It has shown you the number of it. You'll notice that it's slightly slow because files are big. So here it is, 6 windows have come up on the screen. So what are those 6 screens? So the first one, the canvas is called C01. So I'm going to start with C01. I keep these aside for now, and let us focus on C01. So this is my C01. This spectrum, when I did with the draw method, you have already seen it earlier. This is your PSD, that is pulse shape discrimination signal in detector number 1. So see how it worked out. We used the LaTeX method for doing subscript. So it's showing PSD, then down 1. So this is one good feature of in root making these figures. You can actually use LaTeX even for the, I have not shown how to label the axis, so you can label the axis also, and there also LaTeX commands are allowed. So this is my pulse shape discrimination signal. These are the gamma rays, this is the neutrons, and now we must look at the time of flight spectrum in the second graph. So my second graph is showing a time of flight like this. See, very sharp peak. And when we had tried to run it by the draw method, then he had split it up and spoiled the whole thing completely. But this is the actual picture. It is a very, very sharp peak. Why is it so sharp? Well, because the source has been kept very near the detector. So there is no variation in the time, whether even if it's a neutron or a gamma ray, all of them, they reach within the same time. They reach the detector because the distance is only 1 centimeter. So in that much distance, we don't get any separation of neutrons and gamma rays. But they all get combined and we get a single peak. So that was detector number 1. If you look at the second detector, then this is the pulse shape discrimination on second detector. It shows blank. Now you know why. It's because of this auto scaling problem. So we zoom it, and this is what you see. But counts will be less. See, now compared to this one, look, 800 into 10 power 3. So 8 into 10 power 5. Almost 1 million was the scale for this first detector. But this detector only 400. So that is how things work out, because the distance, this inverse square law operates, and you have only this much left from this source if you are to go to such a distance. And so in this distance you get this this PSD. So PSD is this is gamma rays, and from here to here is the neutrons. This is gamma rays and this is neutrons. Now you see the difference between detector 1 and detector 2 is in the time of flight of detector 2. So if you look at the time of flight of detector 2, which again you have to zoom in the usual way, then you see that there is a separation, which was not possible in detector 1. But in detector 2, there is a separation of neutrons and gamma rays. So this is the important thing, and this is due to the distance. Now let's see, if we were to plot on a two-dimensional plot of time of flight versus PSD, then for the first detector it doesn't work, because now the y-axis is time of flight, and along the time of flight is very narrow, because the detector is kept very close to the source, 1 centimeter only. So this whole thing has come compressed into just one sharp line. But along x-axis it is split. So this is gamma rays and this part is neutron. So this part is gamma ray and this part is neutron. But there is no splitting in the y direction, only in the x. But if the distance is proper, like it is so for the second detector, then it looks like this. So this is the actual kind of graph which is expected from all the 100 detectors in a real experiment of NAND. All the 100 spectra will look like this, because the distance of all the detectors will be very large from the source. So here you see that two distinct patches are seen. This left patch, these are the gamma rays, and these are the neutrons. And due to the random coincidences, you see that you also have these things, so you have a spreading out in both in the x direction and y direction. You will see the spreading out. These are arising due to random coincidences. So it means that if you had not done a two-dimensional plot, like suppose if you had only the x-axis, namely only pulse-shaped discrimination, then this tail from the gamma ray, namely this part, would have come inside the projection of this. So if you project these neutrons along the x-axis from here without doing a cut, then it would include this random tail, which is not what is desirable. Similarly, if you were to project it on this axis, then again, although you miss this big peak, but still there is a tail from here. So along this axis also you would run into a problem. So the separation is not perfect till you make a two-dimensional plot of time of flight versus the pulse-shaped discrimination. Both of them are to be used. And to do that, you now have to prepare a banana gate around this. So that is our next step. That's why we did exploratory. We did not go to the directly neutron energy because we haven't yet drawn the banana gate. In order to do the gating on this data, we need to first create a banana gate. Then we have to save it and then we have to use it. So to do that, you need to draw the banana gate. So I am going to zoom it. See, I zoomed it. My interest is to capture only the neutrons, not this tail. And these are also randomly scattered other particles. So I have to focus only on this much. So I must draw a banana gate carefully covering this patch. So you know how to do that. You go into view and then you go into the toolbar, and from the toolbar you choose the scissors cutting and then you click it across this way, and in the last point you just click it again without moving the mouse so that it closes the curve. And having done that, now we are going to apply this cut. So in order to do that, now this is the procedure which has not yet been explained. This is the first time we are explaining how the banana cut. We have explained how to save it, but we haven't explained how really again to use it. This is the lesson today. So this is your banana cut. You right click this cut and then save as, and then you give it a name. So this dialog opens up. He's asking what is the name. So we give a name of this file. Let us call it as neutrons. And we don't need any option, so neutrons, and then you okay, actually you should say neutrons dot capital C, but I think he would have put it in any case. It is always saved as a macro dot C. So I am putting it and then saying okay. So he says that here it is. So he says that the neutrons dot C has been generated and he has saved it. We can see whether that is really the case, and we find that yeah, so it is here. So what is this? Now we have finished the first part, exploration. Our aim of the exploration was actually only just this purpose, to draw this gate around the neutrons and also to check all the other spectra that they were okay. So that we checked it, they were all okay. And then we successfully drew this banana gate around this graphical cut, as they call it in rote. We prepared this graphical cut and then we saved it. Now we have to apply it, and this is the next step. So in a way this work is now completed, so I am in a position to close it. I can actually quit root completely by doing the .q command, and we are finished for the time being the first round of analysis. And in that round we have created this file neutron.c. This was our purpose. So let's see what is this file. Let's double click it, and here I have opened it for you. Let's see, there is some problem here. Yeah, so we have actually saved the wrong thing. This is not the intention. This has saved actually the canvas rather than the banana gate. So there was some mistake in what we did. So let's get rid of it and just repeat it and have it properly done. So I'm going to just repeat. Good for you to repeat it in any case. So root and then execute, explore. Let it take its time, but finally it finishes. So he has finished it. We are only interested in this last one. So what happened is that we didn't position our mouse properly. So let's remove this neutrons.c. Is not we remove it. Move to trash. Okay, so that's gone. Now let's work on this again. So our aim was to draw a banana gate around this. We zoomed it and then options and then view and toolbar and then the scissors tool and then okay. Okay, so you have to actually make sure that the mouse is positioned properly. If I position the mouse in the wrong place and then do the save, then it won't be saving the graphical cut. It will be saving the canvas, which is what happened to me. So I have to make sure that the hand operation, yeah. Now I can see from here that this is the T-cut G that I have selected. Now I should say save as. And then here I should put the name of the file. I wanted to call it as neutrons.c. And nothing in the option and okay it, and then look here, what did he do? So now it is very clear that it is the T-cut G which he has saved. T-cut G has been saved as a macro file and he has saved it. Now let's take a look here. Okay, so this is, yeah, now it is okay. See, that one was wrong, it was showing something else. So this is the T-cut G file. It has got your T-cut G and these are the X and Y coordinates of the points of the polygon. So this is what we got. Now in order to use it, we have to write the next program, and so that will be the final one for the analysis. Our interest is to get the neutron energy, so we are going to do it. I am calling it en.cpp. So there is this another program. We finished with this explore. I can close this root session. So root session is closed, and now I am going to make a new macro. So when I created this macro, I actually copied the previous macro and then added some lines to it. So it's the same as the previous macro, explore, but some extra things are in it. So what is that? Let's see. So I'm opening it for you, and here it is, explore.cpp. So in this, what we do is, this is all same as earlier. The name is changed. The name is explore, so that appears here as well as here. And the spectra, histograms, all are same. I'm going to define some more. So this was explore. So I'm interested in en. So this explore you have seen. I close it for now, and this is your new one, en. So what I do is, I have added up to now we had this much G2. I have added G3, which is going to be the same as G2, but with this banana gate applied to the data. So this is the new one, two-dimensional histogram, but it's going to be gated. You will see how it is gated later on. And similarly, now this part is new. So up to now we never calculated the neutron energy. Now we are going to calculate it. I am going to call it as En, and I am going to make two histograms, one without any gate, which will be wrong. So I have put here question mark, and one will be correct, which will be gated. So in order to see the difference, I have kept both of them. And here I have pasted from the file. So if you take the what I have pasted will differ slightly because I drew the cut earlier and this cut which I am drawing now, that could be different in different number of points or so, but basically coverage is of the same area. So I have taken this part and pasted it there. I can also do it again, but what I am doing is that I am not keeping all the lines. I am not keeping this draw. I don't want to draw it now. I keep all the set points, and this set fill style is not interesting because we are not bothered to fill it. We are not interested in the title. We are not even interested in the variables, but we are interested in this declaration part, and we are definitely interested in all the nodal points. So that much only you paste here. So you take this and you paste this declaration, and here this 13, this refers to the number of data points, number of polygon nodes, and that's all. So I have pasted this much here in the code. So this is the important part. Rest of the code same, but a new part is this. First this one. So here is a new command introduced. It is called as is_inside. So this checks the cut G is the name of that. This, you see, this is cut G. So cut G is that polygon, and this is the point inside the polygon or outside it is decided by this function called is_inside. So while I am inside my event loop, okay, I was already building this spectrum here, G2. Now I build G3 in the exactly identical way. So G2 and G3 are same. There is only one difference. It has got this if qualifier. And this if qualifier says that only if the point ADC 6 17th quantity versus the timing 17th quantity, that is the PSD and T of the second detector, if it is inside the polygon of cut G, then only I do the filling, means updating. Otherwise I do not do anything. So this is the new command. So here it will be the same spectrum which you have seen as this, but it will get cut, and only the part which is inside the polygon will remain. So this is done. Now the only reason for doing this is to make sure that our things are working okay. So we are not interested in this. What we are interested in is neutron energy. So this exercise need not be done, but we are doing it so that we are making sure that we are in the right track. So now I come to neutron energy. Now these formulas are now perhaps easy for you to identify because I had them here for you in the PowerPoint slides. So basically these are the formulas. Basic formulas are given here. We calculate we have the distance, then we calculate the time of flight from this peak, this 2906. I forgot to show you. I'll show you now when we run it, from where we get this number 2906 gamma peak, and the rest of the things I have explained. So this has been coded here. So first we have defined the distance d, then we calculated the time of flight. This is exactly the same formula which I showed you on the slide, and then I calculate the velocity divided by the velocity of light, and then I calculate the neutron energy. So now while calculating the neutron energy, we take care that in case the time of flight is 0, then we will have a problem. So we take care of this here. If the time of flight is positive, that is bigger than 0, then only we calculate the neutron energy by this formula. This is half mv square. But if the time of flight is negative or 0, then we don't do it. We just set the neutron energy as 0. So this is the precaution that we take. And after having taken that precaution, then we fill it. And again we fill it two ways. One in which we unrestrictedly fill. So this will not remove the gamma rays. But what we want is actually second one. This is just for the sake of comparison that we have kept it. It's not essential. But what we really require is this one. So this selects the cut G. That means only the points inside the polygon will be actually taken. and then the spectrum of neutron energy will be built up according to this one. And then we have canvases and we display all of them. That's it. So let's try it out. So I am going to try it out now. So we can run this as a macro. It will be en.cpp. So let's try it out. We'll start root. So root is now running, and then we can execute the macro called as en.c++. So it's now executing, and it takes some time because the files are big, and then he completes the job. So these you have seen before, but I wanted to show you that 2906 from where it comes, and that is in TOF2. So these you have seen all of them. For example, this one you have to zoom, so this you know. So here in this time of flight number 2, this peak of the gamma ray is at that channel number 2902. So this we take as the 0 point of starting. This is the reference peak, so it is at 2902. So this is how we get that number 2902, which you saw in the code. And with reference to this point, how much time the neutron took is the distance from that 2902 up to the point. So that's why we subtract that quantity 2902 from in order to get the neutron energy. So now what I built new is to be shown. So you have seen this graph before. This one is not interesting, so I leave it. I'm going to compare these two. This one is new, this one, and this one you have seen before. So we took this and we applied a gate, and this is the gate which we drew around this. So you see only this data has survived. The rest of the data has got cut out. So this was done only to demonstrate that our cut is correct, that we have not made any mistake. This you should always do, because it is very easy to go wrong in making the cut. So here we have made sure that the cut is correct and only this part of the data is correct. But what we were interested is to have the neutron energy corresponding to this cut. So if you do the neutron energy with that expression half mv square from the time of flight, then this is what you get, this one. But this is without the cut G. What we needed is with the cut G, and that is this. So this is your final answer which we are looking, this window. This is your final answer. And I'm just getting rid of the unwanted windows. So what we were interested to do was to generate the neutron spectrum, and this is the answer. Here also the neutron spectrum got generated, but this was everything including the gamma rays. So